Meet the DCX, Delta Clipper Experimental, a rocket for the people, a revolutionary approach to lowering launch costs, which takes us back to the future of spaceflight, an entirely new philosophy in the development of launch technology. The Delta Clipper team has taken the common sense, tried and true approach of commercial aviation and applied it for the first time to rockets. In early rocket designs, the mass of the equipment and propellant needed to fly long distances was found to be too high. Since the cost of the vehicle was less important than delivering its payload on what was usually a one-way trip, it was decided to throw away those parts of the rocket no longer being used in the flight, progressively making it lighter as it flew towards its target. This is the type of traditional multi-stage vehicle we currently use. Imagine what an airline ticket would cost if each trip started out with an entire plane and ended with only the passenger cabin, and then was rebuilt for the return flight only to be mostly thrown away again. The cost would forever keep flying beyond the grasp of all but a few. That's the situation we face today. We know from experience that we should maintain a mixed fleet of launch capability. But if the goal of our space program is a dramatic reduction in the cost of launching payloads, then it's also time for the next step, a reusable rocket system that operates as routinely as today's military and commercial aircraft. This is why the DCX single-stage rocket is so important. In 1990, the Defense Department selected 4 of the nation's leading aerospace contractors to conduct a Phase 1 feasibility study of the single-stage-to-orbit concept based on available computer, propulsion, and materials technologies. The study's mandate was to answer 3 main questions. Can it be done? Can it be done quickly? And can it be done cheaply? After careful studies by the best minds at each firm, all 4 agreed. The answer to all 3 questions was yes. Single stage to orbit will work. Taking a page from aircraft development programs, Phase 2 of the project was to rapidly prototype X vehicles of increasing size and performance. This aircraft style of development, in which a series of test vehicles are repeatedly flown to incrementally push the envelope of a concept, had never been applied to rockets. First, a 1/3 scale vehicle called DCX would be built to prove the concept and to conduct low-speed flight and maneuvering tests. Next, if funding is made available, will come a vehicle twice the size of the DCX, which will obtain speeds well into the hypersonic range. This vehicle will support commercial and military testing and be our next step on the way to the single-stage-to-orbit fleet, which will be the heart of our 21st century launch industry. In 1991, McDonnell Douglas's Delta Clipper vertical takeoff and landing design was selected for Phase 2, designated the Single Stage Rocket Technology Program, SSRT, to demonstrate technology availability of reusable rocket systems. A suborbital demonstrator was ordered, and an industry team made up of some of the world's top aerospace companies was formed to take on the challenge. These companies, representing some of the best capabilities in the field, contributed vital elements of the program. They too believe that single-stage rocket technology has arrived. In August 1991, at McDonnell Douglas's facility in Huntington Beach, California, the new team was assembled. In keeping with the project's revolutionary nature, a new rapid prototyping environment was created. This X designation and the streamlined project structure provided the right environment for success. Since one of the goals of the project was to incorporate aircraft-like systems wherever possible, top engineers and designers from the successful MD-11 airliner the F-15, the F-18, and the AV-8B Harrier projects were brought in to work together with our rocket engineering staff. Overcoming dozens of technical hurdles, borrowing technology from a wide variety of space, aircraft, and other fields, and creating many new and innovative solutions to the single-stage challenge, the DCX team drove forward to realize their vision, and by early 1993, the vehicle was completed. While the vehicle was being built, a mini spaceport was constructed in White Sands, New Mexico. The spaceport contains everything needed for the DCX flight testing, including maintenance and service technicians required to turn the vehicle around after each flight. The entire DCX flight support team numbers about 35 people. In this small operations van, which is very similar to that planned for the full-size Delta Clipper, only 3 people will be required to launch and fly the vehicle using Macintosh or Windows-like computer interfaces. For its first flight, the DCX will take off and hover just above the ground as its systems are verified. Then it will perform a soft touchdown on its landing gear. Next, it will be flown to higher altitudes and faster speeds in both still and windy conditions, where it will demonstrate its aerodynamic performance. Then it will be flown to several thousand feet, where it will be ordered to pitch over into its landing approach flight path. Next, it will demonstrate its critical rotation maneuver. Finally, using its onboard vehicle management system with its global positioning receiver, the DCX will perform a precision soft landing within 20 feet of its designated touchdown site. In a world ever more conscious of the environment, McDonnell Douglas is proud of the fact that the hydrogen and oxygen propellants used in our DCX will make the Delta Clipper the world's environmentally cleanest spaceship, as its exhaust will be nothing more than water vapor. The Delta Clipper single-stage rocket concept is indeed the door to space for America. Single-stage rocket research bodes a revolution in spaceflight, which will not only give our defenders the technology for global reach, but will pave the way for a whole new generation of scientists, students, and commercial researchers to enjoy unprecedented opportunities for research and exploration. The DCX is as common sense an idea as America itself. This year, the McDonnell Douglas Delta Clipper team will change the world. Single-stage rockets have arrived. DCX, the future is now.
Hello, I'm Pete Conrad, and I was commander of the Apollo 12 moon mission. And I'm here to fill you in on our space program's newest and most exciting mission, a revolution in the way we get to and from space. Our goal is to make access to space so cheap and routine that in your lifetime, we can open this great new frontier to people like you, and America can return to the moon, this time to stay. And this is the first step. It's called the Delta Clipper Experimental, or DCX. This machine is unlike any rocket ever built. It takes off and lands vertically, and it's the first in a series of test rockets that proves technology a step at a time, like we did with Mercury and Gemini before we flew Apollo to the moon. Only this time, the goal is cheap access to space. Here's the problem. Imagine if every time you flew from point to point, your airplane threw away most of its parts during the flight. That's exactly how most of the world's rockets operate, since they were conceived in an age before lightweight composites and other advanced technologies were discovered. It's also one major reason it's so expensive to do anything in space. The DCX is the first step in a new test program to prove the concept of single stage to orbit, or SSTO, which means one piece up, one piece down, like an airplane, eliminating the delay and high cost of putting the craft back together for each flight. And, as you can see by the size of our DCX ground crew, reusable rockets can be maintained by small numbers of people for low-cost operations. I'm sure you've seen the huge control center we used in Apollo and for the Space Shuttle. Well, this is the DCX Flight Operations Control Center. Inside, two of us fly the vehicle using this cockpit, which is modeled after our commercial aircraft displays, another part of our streamlined designs for operations. I say we fly, but in reality, the DCX is so automatic, it flies by itself. And here's an example. On flight number 5, an explosion of some ground equipment ripped a 4 by 15-foot hole in the side of the DCX during liftoff. The vehicle lifted off anyway and was flying its mission on track, demonstrating its robust design. As a precaution, I decided to execute the auto abort sequence, and the vehicle landed safely on the desert floor. If this had been an old-style rocket, it would have crashed or been destroyed. But the DCX demonstrated that SSTO technology allows you to save the vehicle and payload and then push on. On each of the 8 flights of the DCX, we pushed the envelope further and further, learning valuable lessons quickly and at a very low cost to the taxpayers. On the final flight of this series, we rotated the rocket into a nose-down position as if it were returning from space. Then we translated into a tail-first position as if it were preparing to land, a critical maneuver for the next major phase of SSTO development. Like the X-15 behind me, the DCX has made history, leading a revolution in rocket technology. The DCX has completed all of its test objectives on time and on budget. Now it will be modified for continued use as NASA's DCX-A testbed. It will be rebuilt and will fly again in 1996, testing new lightweight components and structures needed for the next and much larger experimental vehicle called the X-33. The NASA-sponsored X-33 is the most important step in the development of this technology for cheap access to space. The X-33 is a rugged, lightweight vehicle which will finish proving the concept of single-stage orbit. It will fly in the spring of 1999, extending the envelope to near-orbital regimes, demonstrating hypersonic and transonic flight, thermal protection, and engine restart. Equally important, it will demonstrate the aircraft-like operations needed to achieve low-cost, full-scale launch systems. The Apollo program gave us a can-do ethic, a first taste of what we will encounter on this new frontier, and it taught us that space offers a whole new future for humanity. And the X-33 project will give us the tools to achieve this great tomorrow. The day when Americans are able to go into space themselves is only a few years away, as routine commercial spaceflight at last moves from dream to a reality.
In August 1991, sponsored by the United States Department of Defense, McDonnell Douglas Aerospace was awarded a competitive bid to design and test a liquid hydrogen, liquid oxygen fueled, fully reusable, single-stage rocket system demonstrator. The result is the Delta Clipper Experimental, or DCX. The design of the DCX included all associated ground servicing, maintenance, and flight control systems. The flight demonstration program would show the aircraft-like operation, autonomous flight control, and low-speed handling characteristics of a vertical takeoff and vertical landing rocket ship. The Delta Clipper Experimental began with the rapid prototyping of a technically complex, one-of-a-kind system by a streamlined, integrated government industry team. It was flying in less than 2 years.
Cylinder drains closed.
10, 9, 8, 7, 6, 5, 4, 3, 2, start.
We have ignition.
We have liftoff.
We have engine throttle up.
Testing of the DCX proceeded along the same lines as conventional aircraft flight testing, continually expanding the flight envelope to cover a new flight or control environment, reaching to discover the unknowns and answer the skeptics by providing real flight and operating experience. The Flight 1 objectives were very simple. Show that vertical landing on Earth works. 150 feet up, across 300 feet, and straight down to a soft landing.
Go on hover. Landing low thrust.
And it did work, even in the presence of 25-knot winds and gusts.
Landing high thrust. Acceleration ramp down. We got a touchdown.
Touchdown. Wait on gear. Engine shut down.
All right.
Flight 2 expanded the envelope.
10, 9, 8, 7, 6, 5, 4. Start and check engines. 2, 1. Launch and flight.
Increasing the altitude to 300 feet. Moving sideways with greater speed.
Landing low thrust. Landing Q limit.
And demonstrating control with another soft landing within 3 feet of the first flight.
Landing high thrust. Cell ramp down. She's looking really good. -6, -4, -3.
Between and during flights, the 8-person ground and 3-person flight crews continually demonstrated that efficient aircraft operations are equally applicable to a rocket ship if it is designed properly from the beginning. For Flight 3, the DCX had to handle its first problem. Helium bubbles in the propellant lines caused the engines to power up with unequal thrust. The DCX tilted as it lifted off. The onboard controls instantly recognized what was happening and quickly straightened the craft. The DCX went on to complete its expanded flight envelope, traveling to an altitude of 1,200 feet, then landing back on its pad again within 3 feet.
Coming into 1,200 feet.
Flight 4 demonstrated the ability to reactivate the entire system and carry out a successful test after being shut down for 9 months.
500 feet.
It also continued the flight envelope expansion, flying to about 2,850 feet above White Sands, at its fastest speeds to date.
Cell ramp down.
The landing pad, by the way, is just concrete, showing that rocket facilities can be simple.
Wait on gear.
The crew then prepared the system for the next flight and were ready to fly within 6 days.
EE, your bottle pressures are about 2,400 psi on both sides.
Okay, it looks beautiful sitting out there. We'd like clearance to send the crew in, please.
You have
20
probably
seconds.
noticed the white clouds surrounding the vehicle at times and blowing away in the winds. These clouds contain some of the hydrogen gas being vented as the DCX propellant lines are chilled down.
7, 6, 5, 4. Start and check engines. 3, 2.
Just at the start of Flight 5, through a combination of unfortunate circumstances, some of this vented hydrogen gas ignited and went into what the engineers call a fast burn. This caused a large overpressure on the side of the DCX, which in turn ripped a hole in its outer skin just as it lifted off.
throttle and.
The DCX flew rock solid. But Pete Conrad, the flight manager, knew there was not supposed to be a hole in the side and commanded the DCX to go into emergency landing procedures, or auto land. The DCX took command, stopping its forward and upward flight, deployed its landing gear, and came back down to land in the desert.
Gears deployed. Rolling up.
They were unplanned demonstrations.
Wait on gear, engine shut down.
But it was clear that rocket ships could be designed to withstand equipment failures, as in Flight 3.
The bird is still vertical.
Or even the massive damage which occurred in this flight, and land safely, be repaired, then fly again. Flight 6 occurred less than a year after the Flight 5 emergency landing. Back on the flight program, the DCX completed the objectives of Flight 5, reaching a higher altitude of 4,350 feet while traveling up and sideways faster, and came down at close to 100 miles per hour. In addition, pitch-over maneuvers, along with the first use of differential throttling and global position satellite data, further expanded the DCX flight envelope. Flight 6 again ended with a safe, soft landing near the center of the pad.
4, 3, 2, 1. Mark vehicle launch. And we have a good vehicle. Airborne for Alpha Charlie.
Flight 7 expanded the altitude, reaching 5,700 feet, and the flight maneuvering boundaries, carrying out a 75-degree reverse pitch-over maneuver. Full roll control was carried out with the gaseous oxygen, gaseous hydrogen reaction control thrusters, and extensive use was made of differential throttling of the main engines for directional control. The DCX descended at a velocity of over 130 miles per hour, again slowing to land in the center of the pad at less than 4 feet per second. Immediately following the landing, the crew rapidly prepared the DCX and ground support for its next flight, and could have flown Flight 8 that afternoon.
Start and check engines. Launch and flight.
Flight 8 completed the chapter on the low-speed handling qualities of the DCX.
Okay, we're at 200 feet.
It flew to an altitude of close to 10,000 feet before reversing its flight direction to begin flying back toward its landing pad, nose first, just as the full-scale rocket ship would when returning from a flight through space.
Out of 2,000. 30 seconds, out of 3,000. Looking good. Out of 4.
A key objective of Flight 8 was to show the controllability of the vehicle as it rotated from its nose-forward attitude during flyback to a base-forward attitude for its vertical landing.
Going into the pitch program, looking good, all the way over, 10 degrees down, coming back. Looking good. Looking good. We're landing low thrust. Landing Q limit. It's looking good. Out of 4,000. Out of 2,000. Out of 1,500.
As in previous flights, the DCX descended vertically to land in the center of the pad.
Landing high thrust.
You're down and lost.
heralding the successful completion of the DCX flight test program and the start of the NASA DCX-A program.
Okay.
The flights of the DCX, coupled with the streamlined ground operations, have provided convincing evidence that America's space program is ready to enter a new era, an era of reusable rocket ships for low-cost, safe, routine flights to, from, and through space. The DCX and DCX-A projects are proving we are ready to take the next step, the NASA X-33 program.
The goal of the Reusable Launch Vehicle Technology Program is to move immediately to mature the technologies essential for a low-cost, commercially developed, and aircraft-like operated launch system at the turn of the century. This is being accomplished through partnerships with industry, with limited government oversight. Government laboratories are providing world-class research and development facilities and critical expertise to the partnership. A radical departure from past launch vehicle programs, the RLV program is industry-led, with both NASA, DoD, and industry contributing resources to the efforts. 3 industry partnerships are currently developing concepts and technologies for the X-33 single-stage to orbit, or SSTO demonstrator. First, Lockheed Martin is pursuing a vertical takeoff, horizontal landing integrated lifting body aerospike engine system. Shown here is the Lockheed Martin X-33 concept being tested in the Rye Canyon Subsonic Wind Tunnel facility. This system is unique in the fact that the airframe and the rocket engine system are fully integrated, requiring extensive wind tunnel and computational analysis. State-of-the-art real-time data acquisition and reduction systems allow for rapid turnaround in concept development. NASA is working in partnership with Lockheed Martin to characterize performance of the highly integrated system using the 14-inch trisonic wind tunnel shown here. In conjunction with wind tunnel testing, extensive computational fluid dynamics analysis is being performed by Marshall Structures and Dynamics Laboratory. This verification will culminate with the hot firing of a subscale lifting body aerospike engine on a NASA Dryden SR-71 in flight during the spring of 1996. Secondly, a vertical takeoff, horizontal landing winged body system is being pursued by the Rockwell team. Rockwell is developing for cyclic testing high-fidelity graphite composite liquid hydrogen tanks. This test program will simulate up to 200 SSTO mission cycles beginning in the spring of 1996. Shown here is the manufacture and testing of insulation integrated with the tank panel under cryogenic conditions. Results to date indicate encouraging breakthroughs in this critical area. Shown here is a Rockwell blanket-type thermal protection system during ArcJet testing at the Ames Research Center that verifies its performance under re-entry conditions. This is intended to replace the primary shuttle-type thermal protection system, which uses thousands of easily damaged manpower-intensive ceramic tiles to protect it from the heat of re-entry. Testing is underway at both the Marshall and Ames hypervelocity impact ranges to characterize the effects of orbital debris on the thermal protection system and underlying structure. In order to simplify the manufacture of aluminum lithium cryogenic tanks, a technique known as friction stir welding is being developed for the X-33 by Rockwell. This simple technique, shown, uses a rotating pin mounted in a milling machine to solid-state weld soft metals together. This is in contrast to the complex, often difficult to repair typical welding procedures currently used on the shuttle external tank. The program will draw on NASA's aluminum lithium alloy experience gained from the super lightweight external tank program. Third, a vertical takeoff, vertical landing concept is being pursued by the McDonnell Douglas Boeing team. McDonnell Douglas is developing a graphite composite liquid hydrogen propellant tank for incorporation into the DCXA vehicle. As a part of this program, several subscale composite cryogenic tank halves were manufactured at Marshall. This footage shows a 32-inch diameter tank half in cryogenic testing to the point of failure. Results to date of the critical portions of the tank have exceeded expectations. McDonnell Douglas is also developing a graphite composite liquid hydrogen feed line, which has been fabricated at NASA. In addition, a composite valve will be integrated with this feed line. This revolutionary approach has the potential for reducing the weights associated with the SSTO's propellant feed system. Seen here is the most recent flight of the DCX. The DCX-A, or Advanced, will incorporate SSTO advanced technologies. These include the graphite composite liquid hydrogen tank and composite feed line and valve shown earlier, as well as an aluminum lithium liquid oxygen tank, composite intertank structure, and new auxiliary propulsion system. This will provide an early indication of how these technologies perform in real-world environments. Flight is scheduled for the summer of 1996. The X-34 is being built in partnership with the Orbital Sciences Corporation. The X-34 will be used to investigate technologies that may be incorporated into future reusable launch vehicles in hypersonic environments. It will be launched off the NASA shuttle carrier aircraft 747. One of the candidate booster engines is the Russian RD-120. One of these engines was received in June of 1995 at the Pratt & Whitney facility in West Palm Beach for a series of tests. As an example of the partnership with industry, NASA is responsible for development and delivery of the X-34 upper stage main propulsion system. In support of this, the low-cost simplex turbopump will be utilized as shown here in this computer-aided design representation. A representative upper stage engine combustion chamber is shown here, being wound on a mandrel at Marshall to demonstrate producibility. The 12,000-pound thrust combustion chamber is undergoing hot fire testing at NASA to provide engineering data to support the X-34 upper stage engine development. A partnership with Rocketdyne is maturing technologies associated with two different propulsion concepts. The first is an evolution of the Space Shuttle main engine, which could potentially support the Rockwell or McDonnell Douglas SSTO concepts. Tests are being conducted to explore the limits of the SSME operating envelope using the technology test bed at Marshall. Evolution of the SSME could include advanced nozzle concepts, which are supported by computational fluid dynamics analysis, cold flow tests, and wind tunnel tests conducted at NASA. The final step in the SSME evolution process would be conversion to an oxygen-rich full-flow cycle. A small-scale oxidizer-rich preburner designed and fabricated by Rocketdyne is shown here in a recent hot fire test at Marshall. The second Rocketdyne engine concept is the linear aerospike. This engine could be used by the Lockheed Martin Skunk Works. Versions of the linear aerospike engine were tested by Rocketdyne in the early 1970s. This concept is also supported by computational and wind tunnel analysis at NASA. One new technology required by this engine is the use of modular thrusters. These combustion devices incorporate rapid prototyping as a means of assessing design options to arrive at the most cost-effective concept. United Technologies Pratt & Whitney has teamed up with the Russian company NPO Energomash to promote the development of engine concepts. This effort includes the development and test of a subscale tripropellant injector rig in Russia. Bipropellant engine concepts, which utilize the hydrogen and oxidizer turbopumps developed in the SSME alternate turbopump program, will be matured through the Space Shuttle program. The SSME ATD turbopumps will be combined with the mature component designs available through the MPO Energomash. A cooperative agreement is in place with GenCorp's Aerojet and their partner, Chemical Automatics Design Bureau from Russia. Several tripropellant preburner element designs have been tested at CADB's facilities in Russia. The final design is being incorporated into a full-scale tripropellant preburner. The CADB RD-0120 liquid hydrogen, liquid oxygen engine has successfully flown on 2 occasions on the Russian Energia. Current plans are to demonstrate life improvements and operability features of this engine at NASA. An evolved RD-0120 could potentially support the Rockwell or McDonnell Douglas SSTO concepts. Operability improvements will include advanced electromechanical actuators and advanced controls and diagnostics avionics. To more fully understand the physics associated with oxidizer-rich preburners, tripropellant main injectors, and gas-gas main injectors, a cooperative agreement is in place with Penn State University. Numerous injector element designs are tested in Penn State's combustion lab using faculty and graduate students. The Penn State work is supplemented with computational fluid dynamics analysis at NASA. Cooperative agreements with 2 small companies, Fiber Materials Inc. and Refractory Composites Inc., will determine the potential use of composite materials for liquid rocket nozzle extensions. The RLV technology program philosophy is to build a little, test a little. Hundreds of hardware demonstrations are currently underway that will make tests of X-flight vehicles possible. Continued industry government partnerships are crucial to its success. The RLV technology program, partnerships for space launch leadership.
Premiering this
As we accelerate toward the 21st century, the United States aerospace industry is challenging the world with the X-33 and the reusable launch vehicle. Only the lowest cost, most robust systems will survive the competition. One rocket propulsion system offers the right combination of performance and cost, the Aerospike engine. As we accelerate toward the 21st century, the United States aerospace industry is challenging the world with the X-33 and the reusable launch vehicle. Only the lowest cost, most robust systems will survive the competition. One rocket propulsion system offers the right combination of performance and cost, the Aerospike engine. Its unique shape, highly integrated with the vehicle, and simple gas generator cycle enables the highest performance, lowest cost vehicle to be developed. The Aerospike is a mature engine concept with over $500 million invested to date by NASA and Rocketdyne. Its performance and operation have been verified by over 73 engine hot fire tests and 4,000 seconds of operation. In the early 70s, the Aerospike was a leading candidate for the Space Shuttle main engine. Starting in the late 1960s, Rocketdyne and NASA began developing the Aerospike engine. Testing was performed at all levels. The thrust cell shown here is a key component of the engine, where the propellants are mixed and ignited to produce thrust. Each cell develops a fraction of the total engine thrust. This allows the engine to be developed at a small size, thus lowering risk and cost. Multiple thrusters are then clustered on the Aerospike nozzle to create the required thrust level. The Aerospike is similar to other rocket engines, except that it has a very high efficiency nozzle. The nozzle is a truncated spike which directs the flow of high-pressure gases coming from the thrust cells. The gases expand against the surface of the nozzle to produce thrust, then continue to expand to enclose a subsonic, recirculating flow field at the base. Pressure from this flow field acts upon the base and produces additional thrust. Turbine exhaust gases are also discharged to the base to add thrust. These flows combine to produce very high nozzle efficiency, a major advantage of the Aerospike. Another major feature is altitude compensation. This is provided by the outer free jet boundary of the primary flow. At sea level conditions, the boundary is compressed, increasing pressure on the nozzle wall and base. As altitude increases, the boundary expands, keeping nozzle performance near the theoretical maximum for each altitude. Finally, the Aerospike's design also provides size and weight savings when compared to conventional Bell engines. Testing of linear Aerospike engines was initiated in September of 1971. 8 ignition and transient tests were conducted to develop a reliable start envelope. 25 tests were conducted with a combustion wave ignition system, which consisted of a central premixer, which initiated a detonation wave for simultaneous ignition of all thruster elements. The first linear engine used J2S turbomachinery and related hardware, had 20 thrust cells and produced 250,000 pounds of thrust. A total of 44 tests and 3,114 seconds of main stage operation was achieved during the test program, with one test running for 592 seconds. The test successfully mapped the engine's operational range, including chamber pressures from 680 to 1,250 psia and mixture ratios from 3.2 to 5.6. The second linear engine initiated testing in 1972. It also used J2S turbomachinery and related hardware, but had 10 thrust cells and produced 125,000 pounds of thrust. Nearly 30 tests and 1,000 seconds of operation were accumulated on this engine, including dynamic hinging of plus or minus 16 degrees and an assessment of thrust vector control using differential throttling. The Aerospike is the right engine for the 21st century. No other engine has the unique combination of very high performance and simple gas generator cycle as does the Aerospike. It allows the smallest, least expensive vehicle to be developed. With over $500 million invested to date and thousands of seconds of engine hot fire tests, the Aerospike is ready to become the rocket propulsion system for the next century.
Engine chill and final bit. Mark 1 minute. Fans are off, heaters are off, and we have engine out, monitoring, launch commit process initiated. 50 seconds. Seconds. Looking good. 25. 15. 10. 9. 8. 7. 6. 5. 4. 3. Start and check engines. 2. 1, flight commit. Got a roll program out of 500 feet. Roll's complete, looking good. 1,500 feet. Pitch maneuver. Ascent trim AOA, 10 feet a second forward. 20 feet, 30 feet, 40 feet a second, 50, 55 feet, pitch maneuver, out of 2,500 feet, okay, 0 feet per second, turning around. Minus 20, minus 30, minus 40, coming back. Looking really good. It's looking good. Coming to a pitch maneuver to stop. Landing low thrust.
Engine throttle down.
Landing Q limit, 72 feet a minute. (2,000 feet). (1,500 feet). It's out of 1,000 and it's looking good. 600, 500, 400, landing high thrust, 300.
The gear is down. Gear is down.
Landing high thrust, landing accel ramp down. Landing small negative.
Wait on gear. Wait on gear. All systems look nominal. EE, your bottle pressures are about 2,400 psi on both sides.
Okay, it looks beautiful sitting out there. We'd like clearance to send the crew in, please. (103). Engine chill and final bit. Mark 1 minute. Fans are off, heaters are off, and we have engine out, monitoring, launch commit process initiated. 50 seconds. Seconds. Looking good. 25. 15. 10. 9. 8. 7. 6. 5. 4. 3. Start and check engines. 2. 1, flight commit. Got a roll program 2,500 feet. Rolls complete, looking good. 1,500 feet. Pitch maneuver. Ascent trim AOA, 10 feet a second forward. 20 feet. 30 feet. 40 feet a second. 50, 55 feet. Pitch maneuver. Out of 2,500 feet. Okay, 0 feet per second, turning around. Minus 20, minus 30, minus 40, coming back. Looking really good. It's looking good. Coming to a pitch maneuver to stop. Landing low thrust.
Engine throttle down.
Landing Q limit, 72 feet a minute. 2,000 feet. $1,500 feet. Out of 1,000 and it's looking good. 600, 500, 400, landing high thrust, 300.
The gear
Down.
Gear is down.
Landing high thrust, landing accel ramp down. Landing small negative.
Wait on gear.
Wait on gear.
All systems look nominal.
EE, your bottle pressures are about 2,400 psi on both sides.
Yeah, it looks beautiful sitting out there. We'd like clearance to send the crew in, please. Seconds. 15. 10, 9, 9, 8, 7, 6, 5, 4. Start and check engines. 3, 2, 1. Launch and flight.
Engine throttle up.
Looking good out of 100 feet. They got a pitch program.
You have an auto land? Gears deployed. Throttling up. Wait on gear, engine shut down. The bird is still vertical.
Shell and final bit. Launch commit process initiated. Port command has been armed. Flight limits. Seconds. DM bid, ground pass, table pass. Heaters are off, fans are off. 30 seconds.
Starting to get a whole bunch of vapor from the pre-cooling the engines. Probably see that light off. Nice little orange flash around the face of the vehicle when the engines actually go.
10, 9, 8, 7, 6, 5, 4. Start, check engines. 3, 2, 1. Launch and flight. Engine throttle up. Looking good out of 100 feet. They got a pitch program.
And about 15 seconds later, we're able to hear the engines. 3 miles off, about that much delay. Nice little concussion at the start. That wild guess, that was gas around the face of the vehicle lighting off. Down again.
Wait on gear, engine shut down. Bird still vertical.
Their shoes back on the ground. Engine shut down okay. And there's the pad crew heading on down the road.
Birds on the ground, okay. Okay, everything looks good.
And with a little bit of luck, in a half hour or so, we'll be able to go down and get a close-up look at her on the pad. They're saying they're going to let a busload of us down there who are interested enough to stick around and take a look. Probably get you some video of that.
Range control, flight. Okay, we had an auto land in the desert. Everything's okay. No fire.
I'm sorry. No, I just listened to that. Yeah, so I think that's what. You remember Flight 4 was an extra 60 seconds or so. So we found a bias that we would put in something kind of stuff. So if you look for where the flight station is, you're right down the square, right down the line to hit it. Perfect as far as one way or the other. You'll get the fountain effect coming up as it comes down, and that's why you get some close to
you basically blew the dust off the top of the desert and then gouged for foot deep, couple feet round holes.
Yeah.
Did you bake any of this pretty well? Sorry.
After we landed, and we were dumping our about 9 inches. So after we landed, then the vehicle didn't know it had been hurt. Okay.
Yeah.
It did not know it had been hurt. So it went through its normal venting sequence and all that stuff. So by the time we came out with our recovery team, again, the vehicle appeared to be normal. All the pressures were right and everything. So the first thing we do then is we start dumping LOX and hydrogen. We put the elephant trunk on and put the hydrogen, dumping it through a vent, and then the LOX is just dumped through the engine. And we kept LOX in there. The LOX wouldn't boil off, and the temperature was almost 120 degrees, and it stayed in there about 3 hours. Wow. That shows you how good insulator you got here. Yeah. But the point is that a lot of this stuff is discoloration to the fact it's been, but it's still a little moist, you can feel it. Yeah. That's because it's had LOX in it. And LOX?
Yeah. Yeah. But if you reach down and pick a little piece off,
yeah,
it crumbles.
Crumbling.
Yeah. So it's not classified or anything.
But again, if you do guidance and control, it just works beautifully.
I could see that the south side of the bird was really ragged.
Yeah.
Yeah, that's for sure.
Yes.
Well, that's the next thing we're going to show you.
We're going to show you the north side, Harry.
Take all the pictures of the north side we want, right?
Yeah.
You can, anything you want at northeast, south, and west is okay. Northeast and west, we won't show you the south.
south side of the DCX pretty much as she landed. She's still sitting in the same orientation as she took off and flew. Just came back over from the landing site. Looks like the bottom body flap's gone, plus a whole bunch of the side of the aero shell. We understand the machinery inside works fine. There were no instrument indications there was anything wrong at all in the control hut. Oops, somebody coming up behind me now.
Wide angle lens doesn't show a lot of detail.
Yeah.
Whatever that word. That's why we're up there.
Yeah.
Just if you're allowing external views.
These are some of the pieces that came off DCX. Laid out here in the pavement.
I don't want to get them inside. Let's talk about the picture. That's fine. Anyway,
Well, you can walk up.
walk up to it. I just don't want you poking your camera inside. Is what I'm saying.
Okay.
I would agree with you.
Okay.
Got a good look inside. Pardon?
Thanks.
Yeah, we're saying it's about 4 feet wide by about 6 feet. We haven't got a full figure on it. What you may want to do is get both sides, because it's the contrast. The other side, you can't tell there's anything wrong.
Got a point there. And I understand the instruments on the way back down said there wasn't anything wrong either as far as the vehicle systems went.
That's correct, isn't it?
Yeah.
And this looks like the body flap came off during the flight. Laid out on top of the wooden.
We took that off.
Oh, you took that off. That was still on when you landed then. That was still on when you landed then. Okay, it was hard to tell.
We took it off.
That's the inside.
Yeah, it looks a little too clean to come off on its own.
Well, the question was, will it go on automatic or not? You have to wait on it. It said wait another minute.
Yeah.
Because it's supposed to be 5 minutes, and sure enough, at 5 minutes, then
We have some time to sit down and talk when we get back to the
sure, the
office.
question, when are the rest supposed to come on?
Acting like he wasn't even armed. So we had to abort it. It was about to do it itself. So,
You're looking at it.
The vehicle from the east side at this point, looking pretty much back towards the visitor observation site where we watched her fly from yesterday. So damage side is on the left, on the south. Damage seems to be pretty much superficial. It's essentially the aeroshell, which, as you may have seen earlier, is pretty lightweight graphic epoxy material. The internals of the machine seem to be in pretty good shape. As we said earlier, there was no indication on the instruments that any of the systems had any problem. They had to tell the pilot, Pete Conrad, that it was time to go over to the auto land mode and cut this test short. We heard somebody mentioning earlier that they kicked in auto land at about, I believe it was 1,200 feet. And the vehicle coasted on up to 2,600 feet or so before it began its descent. And ended up coming down off to the west of the launch stand. This is, in fact, the launch stand that it's sitting on here, so I'm told. I'm going to go around and take a look at it from the north side now. It'll look practically undamaged from there. Practically speaking, it is undamaged. It mainly seems to need a new aeroshell. And this one doesn't look real repairable to me from here. The X from the northwest corner. As you can see from here, it looks pretty much undamaged. The only thing you can see at all is a little bit of scorching along the west side of the vehicle, stronger on the south side. At least in part, that's just the normal hydrogen burn-off, that engine light off. The wind was from the north to the south at about 5 knots during the launch. Most of the hydrogen venting was going mostly to the south of the vehicle. And in fact, that scorching would be perfectly normal for this launch. Running about halfway up. Basically, they can just scrub that off the aeroshell. Whether they bother, whether they keep this aeroshell or build a new one, remains to be seen. take a close look up under the north side body flap there. Scan to the west side body flap. And then up along the vehicle edge. Yeah, you can see a crack in the aero shell there, peeled back a little bit, obviously. There were pieces of it flapping in the breeze and peeling loose as the vehicle went up and then came down again. Do a pan to the right off to the north and just take a look. Slow look at the ground support equipment that's scattered around here. Most of it seems to be over here up to the north of the pad. Cryo trailer of some sort there. Can't see on the viewfinder, but there'll probably be information on the tape that'll tell us whether that's nitrogen, liquid hydrogen, or liquid oxygen. Stand back a bit. During this generator and support equipment trailers. I believe these are lightning rod towers. We do get a lot of thunderstorms in the summer around here. They may also be antennas, but I expect they do double duty.
Well, this is our support gear over here, and then this normal location.
Yeah. Here's the portable shelter that DCX would normally live in while it's sitting out here. Keep some of the sand and sun out.
It's on bogies, and we pull it back over.
Oh yeah. You got wheels down there. You can just tow this whole thing around.
Yeah, it pulls around just like a wagon train.
I assume you'd have it staked down in between times against windstorms coming through and stuff.
Now that's capable. Those bogies are filled with concrete.
Ah, okay. That'll stake it down pretty solid.
You can't see the other one. And
don't let it run over your toes.
Boy, that's for sure. It's designed to stand 100-mile-an-hour wind. And I think it's been there.
I understand it got a chance to right before the first flight. There was a storm that came through and tore things up a little bit, right? Stoked everything down, is the story I heard. Managed to fly in spite of that.
Flight commit. Hey, it's coming right out. Pitch program, looking good. Retracted.
outstanding job, and the vehicle did an outstanding job, and we'll have it turned around, ready to go. The only reason we're not going to fly before our next flight date is so we can look at our data on our flight guidance and make sure we're clear to go do our next flight, which will expand the envelope even further, taking us up to our highest descent rate of minus 200 feet and some higher sideways velocities, and that will give us the kind of data that we need to go do our pitch maneuver and complete the flight test on this particular vehicle. So if you want to come back, we'll be ready to fly on our next flight date. Thanks.
Gentlemen, that concludes our program for today. All the folks that are on my bus, please go ahead over there, and we'll be ready to go here momentarily. Okay, all the members of the media, please just hang on. We need to take a look and see who wants to stay.
The blue lines are lines which are presently being drained. The orange lines are presently in a purge state. It shows tank pressures, temperatures, valve conditions. So this is how we control the bird with these three screens. You got the flight manager screen, you've got a deputy flight manager, he's controlling the bird right now, and then the ground systems are on the third screen. I'd like to walk over here and place this one back. See you right back.
And you were talking about the possibility that one of the future developments of this might be a nose-first descent through part of the atmosphere and then the vertical land.
That's what this is.
And we're going to do that 2 flights from now.
Oh, okay. I didn't realize that was actually
That's the one
going to happen.
It's still subsonic, but it will demonstrate the rotation of this vehicle and then vertical landing.
What's the
we'll
altitude?
We'll actually go through 180-degree angle of attack rotation from a 15-degree pitch down attitude.
And what's the altitude going to be on that flight?
Well, it's higher than this, probably twice as high, somewhere in that range.
And what's the plan for the next flight then?
Well, the next flight, we're going to go through, this one was a 15-degree constant angle of attack. The way we got that is we take off vertically, and then we gimbal the engines and start going this way. Net angle of attack, nose to velocity vector is 15 degrees all the way up, and then back over and then down.
Okay.
The next flight, we're actually going to sweep through a 0 to 70 degree angle of attack, and we'll actually pitch 35 degree off of vertical and get up to altitude, translate over and land again. And so that's basically the plan. The last flight will actually go up and then pitch down and rotate and come back.
Okay. Now, is the next flight, is that going to be similar altitude to this flight then? Just a different pitch angle? Oh, it will still be higher.
It'll be a little higher.
Okay. And the ultimate altitude is going to be like 8,000 or 9,000 feet. Is that what the plan is?
Yes. So.
Do they envision it's just going to be a 3-flight series, or do you think this is going to go to 4 flights?
It'll be 3 or 4 flights. So we'll see how that all works out.
Yeah. So by mid-July we should be finished.
We're discussing that right now.
Okay.
Surprisingly.
How was the major component delivery for the XA going?
The hydrogen tank is going real well. The inner tank is in good shape. It'll be available this summer. The Russian tank has fallen behind. We're still trying to assess how far behind. The APS is in excellent shape. We've run all the components up at Aerojet in Sacramento, and we're bolting those together on a dummy structure in the next month. We'll be running them all.
Sorry, the APS?
Auxiliary Power System. It's all together too. We have all the parts for it. So the only thing that's questionable right now is the Russian tank.
This is the Flight Operations Control Center.
Oh, yeah? For some reason we have to get here.
News console's along here. Far end is vehicle ground management, and here end is where they actually run it in the flight. I believe that middle one there is where.
Yeah, basically, we just have 3 people. The 4th slot where Jim's sitting is for the program manager to sit, and it has no controls or anything. It's monitor only. It's basically, it could be used as a hot spare too. If for some reason our computer died here or something, we can jump in there and start using it as a hot spare. And then all our systems all in the racks. So we have a telemetry in the middle here. Basically, we have telemetry information and ground support equipment information. And our system is several computers that are linked over Ethernet. So we basically passing it over Ethernet. And like down here in our HP systems here, we have an archival system, so we record every command, every mouse click, all the telemetry coming in. Matter of fact, what Jim's doing it right now is plotting out all the data from the flight. He's already plotted 200 plus or so already. The company that developed this portion of it was, I'm from McDonnell, it's the Kennedy Space Center. And the Kennedy Space Center division did this portion of the FOCC. We call it the RTDS, data systems. And what we did is, the Kennedy Space Center, McDonnell Douglas, does payload processing for the space shuttle. And they had a system we developed for NASA in the operations checkout building. And we basically took that generic system and bought new, kind of bought a copy of it, and then customized it with all these displays here. So all this equipment here would be identical to something you've been seeing at the operations checkout building over at the Kennedy Space Center. So we had a group of 10 people that developed it. I'm software, and the hardware person. We've been out here on basically when we shipped from Kennedy Space Center, we came with it. And we've been here making real-time, rapid prototyping changes as we build everything. We automate it. Basically, our computer's right there in the rack. The simulator here allows us to check everything. As we make our changes, we can simulate it. Check out the everything is controlled with the mouse. I'm sure you've seen it over there if you're watching the screens. We do have a backup system right here, where if our system, unfortunately the way that this system is built is single string, so if any computer fails, we're in trouble. And basically, this is our backup. Hardwired. Coming up on 17 minus 30 seconds, Mark. 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, Mark. T0 plus count follow. Access to space, plus 5. We hope to keep it at 3 or 4 if we can, so we're kind of pushing for it. We'll see as we design the vehicle how we can meet that goal or not. But we get Tom Ingersoll, who's the deputy flight manager, is the McDonnell Douglas, the operations lead for the X-33 now. So he's been working DCX all along. Now he's working X-33, so he's hopefully take all the lessons learned here.
I'm pretty sure it's where Pete Conrad sits during the flight.
Same with Pete.
Tom Ingersoll.
And we're working on the X-33 also. So flight manager. Pete calls all the shots in here.
You got it all explained?
Yeah. I don't know about that. It's showing on the RTDS here.
How long have you been on the program?
Me?
Yeah.
I transferred from St. Louis back to Huntington Beach in May of 1990. Bill Gava said, "We're working on this program." And I said, "Count me in."
All right.
I've been here ever since.
All right.
It's almost 5 years. Right, it's 5 years.
And you are going on to the X-33?
You bet.
Yeah. See where the areas
guy coming back to give us the word whether we can get out to the pad. That's the MacTac White Sands ground crew out there, pretty much checking out the vehicle, make sure it's safe for us to go out and have a look.
Well, you might have ended up that way a few hundred feet.
At its landing site, it came down less than a couple of hours ago. It's only been safe to approach since they finished dumping the fuel for about a half an hour now. See the scorch marks from the vented hydrogen lighting off it, lift off there. Upwind side of the vehicle, not much scorching at all. We're on the southwest corner of the vehicle here, up towards the northeast. There are a whole bunch of people standing around, VIPs, spectators, news types, and there's maybe a half dozen guys who actually lay hand on the vehicle when it's being serviced. I understand there's actually a grand total of 7 people who lay wrench to it in a routine, and actually move the DCX back to its launch stand. Take a look. Man, that heavy cast fixture there. There's one been bolted onto each corner of the vehicle. It does not usually fly with that. I think that those are attach points for the crane. Not going to be a crane, that's just a ground transporter. Not sure how this works. We'll have to see if we can get some shots of it. I think they may just slide it up around there, jack it up a little bit, or possibly let the landing legs down and lower it onto that, at which point they can tow it. Have to wait and see. The launch stand, not to mention lens cap flying around in the breeze. DCX took off from just a few hours ago. We're looking down at the south side of the launch stand here. And that line there is probably where the air vent was, where they had the problem with the explosion last year. Looks like fueling lines and so on along here. Stand around here much longer, we're going to get our butts run over since they're actually working here live. See if we can see anything about how these fixtures actually work. Because I understand there's hydraulic jacks on the transporter there that are used to lift the vehicle up off its feet once they've got all 4 of those fixtures hooked up and lined up. I just heard somebody saying, okay, coming up. Basically, once they've got it up on this transporter, they simply hook a tractor up in the front of it and tow it back over to the launch stand. Here there's some rigmarole involving jacking it a couple of times and putting wooden blocks in between the supports to get it up high enough to get it back on the launch stand. We'll go. And sure enough, it looks like we are. Tow speed 5 miles an hour, load capacity 24,000 pounds. DCX being a boilerplate vehicle, its ratio between its dry tank's weight and fully fueled weight is more like 2 to 1 instead of about the 8 to 1 an orbital vehicle would take. Fairly hefty piece of machinery there for its size. An actual orbital vehicle, proportionate to its size, would probably be much easier to move around in the ground once the tanks are empty. Go. As you can see, nothing fancy, just a half dozen guys doing the job and making sure it gets done right. You need to keep the cables lined up, just have somebody there and hold them. Going to a couple hundred yards away, actually I think 350 feet away. That's the launch stand out there. Probably going to be a while before it actually gets there. Watching it go the whole way would probably be approximately like watching paint dry. So we'll give it another minute here and then.
Start, check engine, launch and flight. We have engine throttle up.
God almighty, that's beautiful.
Flip flop position 1. Pitch program. Flip flop position 2. Out of 2,000. Left one deployed. 30 seconds out of 3,000. Looking good.